Good evening, sir.
System.
Good evening, sir.
Yeah, good evening, Appa. Just a minute. Something has happened here. Just a minute. Yeah, can you see the screen sharing? Ajay?
Yes, sir.
Okay, because some problem is there in the desktop today. So I'm taking in the tab only for today's class. Appa. By this class, I will make that corrections on all those things. Okay.
Yes, sir.
Yeah. Now we have completed the concept of the dual nature in the last session. Isn't it, Dhanlakshmi?
Yes, sir.
Yeah. So today we'll take up the new chapter, that is atoms. Yeah. Now you know that basically atom consists of protons, electrons, and the neutrons. And this proton contains equal number of protons and the equal number of electrons. So this atom is going to be electrically neutral. Atom is going to be what? Electrically neutral. In order to explain the structure of the atom, the various theories were developed. The first one is the J.J. Thomson atomic model. The second one is Bohr's atomic model. And the alpha scattering experiment, or we can consider it as a Rutherford atomic model. So these are the three models which we are analyzing to explain the structure of the atom. The first one is the J.J. Thomson atomic model. The second one is the Rutherford alpha scattering model. The third one is the Bohr's atomic model. Now, what is the J.J. Thomson atomic model tells? Suppose if I considered an atom, in this atom, the entire mass of the atom is uniformly distributed. The entire mass of the atom is uniformly distributed throughout the entire surface. So throughout the entire surface, the mass is going to be distributed, and here and there the electrons are going to be embedded like a seeds in watermelon. So this is called the negative charge, and the shaded one, that is called the entire mass is distributed uniformly. So according to the J.J. Thomson atomic model, the entire mass of the atom is uniformly distributed and negatively charged here and there are embedded like seeds in watermelon. This is what the J.J. Thomson atomic model tells. By using this J.J. Thomson atomic model, we can explain the concept of the thermionic emission, that is the emission of electron because of the heating process. And also we can explain the photoelectric emission. And also we can explain the concept of ionization. Ionization means the removal of an electron. Now, this J.J. Thomson couldn't explain the structure of the spectral lines in hydrogen and other than the hydrogen atoms. And also it couldn't explain the concept of the scattering of alpha particles. So the scattering of alpha particle couldn't explain by the Bohr's theory, J.J. Thomson. And the spectral series couldn't explain by the J.J. Thomson atomic model. So these are the drawbacks of the J.J. Thomson atomic model. So in order to correct this, another scientist called by the name Rutherford has explained the structure of the atom by considering the alpha scattering experiment. What is this alpha scattering experiment tells? Look at this. He has considered an atom. According to the Rutherford, the entire mass of the atom is concentrated at the center. The entire mass is not uniformly distributed. Entire mass of the atom is concentrated at the center. That is called as the nucleus. And whatever the electrons are there, that electrons are going to revolve around the nucleus in a circular path. So according to Rutherford's atomic model, the entire mass of the atom is concentrated at the center called nucleus, and negatively charged electrons are revolving around the nucleus in the circular path. This is what the Rutherford model tells. But how to conclude that the entire mass of the atom is not concentrated? It is completely empty according to Rutherford. How to conclude this? To conclude that, he is conducting an alpha scattering experiment. He is going to send the alpha particles. He has noticed that maximum alpha particle pass inside the atom. When alpha particle passes inside the atom, you know that alpha particle is helium nuclei 2He4. Alpha particle is the helium nuclei 2He4. and this is positively charged. If the entire mass is distributed uniformly, alpha particle should not come out of the other side. It should get absorbed or it should get reflected. But we have noticed that the maximum of the alpha particles has passed straight without any deviation. That indicates the most of the atom is empty. Most of the space of the atom is empty. But the entire mass is distributed uniformly, no? And it is at the center. So whenever the alpha particle is moving exactly at the center, it will stop at one particular point and it will repel back. Why it is going to repel back? Because according to the Rutherford, entire mass is concentrated at the center, and this alpha particle and this particular point are going to get repelled back. These two are going to repelled back because of the repulsion. So that clearly tells the entire mass of the atom is concentrated at the center. Entire mass of the atom is concentrated at the center. Only few of alpha particles is going to get scattered by more than 1 degree. It is going to scatter by more than 1 degree. Only a few particles is going to scatter by more than 90 degree. That is only 1 in 10,000. I mean 1,000. But a very few particles will get scattered by 180 degree. Only a very few particles, which is like almost one atom, is going to scatter by more than 180 degree. So if you want to find the number of the scattered alpha particles, by knowing the scattering angle theta, by what angle it get deflected, by knowing that angle theta, you can find the number of the scattered particles. That number of scattered particles is inversely proportional to sine power 4 theta by 2. Remember this. Number of alpha particles scattered is inversely proportional to the sine power 4 into theta by 2. So if you plot the graph between theta versus the number of scattered of alpha particles, it is going to be like an exponential decreasing like this. So this is the nature of the graph for the number of alpha particles versus the scattering angle. Yes. Come to the next very important concept, Appa. That is distance of closest approach and what is the meaning of the impact parameter. Yes. If I consider an atom, let us say this is the atom. What is the central part of the atom called? What is the central part of the atom called? The nucleus.
Nucleus, sir.
Yeah. Now I'm going to incident with the alpha particle exactly opposite to that. Alpha particle. Now as this alpha particle moves, at one particular point it has to stop, right? Why it has to stop? Because this is positive charge. Alpha particle is also positive charge, so it has to get repelled back. So at one particular point where the alpha particle is coming to rest, at that point velocity will be completely zero. Velocity of the alpha particle at that point will be zero. At that point, all kinetic energy is converted into a potential energy. So at which point the velocity of the alpha particle comes to zero, from that point to the nucleus, is what we call as the distance of closest approach denoted with R naught. So what is distance of closest approach? It is the distance. It is the distance from the nucleus to the point. From the nucleus to the point at which velocity of the alpha particle will be equal to what? 0. Or potential energy is equal to what? Kinetic energy. So if I equate that potential energy and kinetic energy are equal, then I will get the formula for the distance of closest approach as 1 by 4 pi epsilon naught into Z E squared divided by E, where E represents the kinetic energy of mv square. Of mv square. So what is the formula for the distance of closest approach? Distance of closest approach is equal to 1 by 4 pi epsilon naught into Z E squared divided by capital E. This is the distance of closest approach. Any doubt in the distance of closest approach?
No, sir.
Okay. So let us consider the central part of the atom as nucleus. This is the central line of the nucleus. Now, I'm going to incident the alpha particle. I'm going to incident the alpha particle with the velocity v. Now, whenever this alpha particle is incident with the velocity v, whatever the maximum perpendicular distance we have between this initial velocity of the alpha particle and the central line of the nucleus, this perpendicular distance is what we called as the impact parameter b. So what is impact parameter b? The perpendicular distance. What is impact parameter b? Perpendicular distance between the initial velocity vector of the alpha particle from the central line of the nucleus. From the central line of the nucleus to the initial velocity of the projection of the alpha particle, this perpendicular distance is what we called as the impact parameter. And please remember that impact parameter is given by the formula Z E squared into cot theta by 2 divided by 4 pi epsilon naught into kinetic energy, or you can take it as E. That E represents of mv squared. So remember that formula for the impact parameter. How that impact parameter and the cot theta by 2 are related? How that impact parameter and cot theta by 2 are related? Directly proportional, right? Now, if T is the thickness of the foil, if you are using one thin gold foil in the alpha scattering experiment, if T is the thickness of the foil and N is the number of alpha particles scattered, keeping the same scattering angle theta as constant, we can observe that number of scattered alpha particle is directly proportional to the thickness of the foil. As the thickness of the foil increases, the number of scattered alpha particles also increases. So N is directly proportional to T. Or you can say, if you are keeping the different thickness of the foil, then N1 by N2 will be equal to what? T1 divided by T2. So remember this, the number of scattered alpha particle is directly proportional to the thickness of the gold foil. More the thickness of the gold foil, you can notice more number of scattered alpha particles. So N1 by N2 is equal to what? T1 divided by T2. Come to the concept of the Bohr's postulate. What is the Bohr's postulate tells? Now, if I consider an atom, what is the central portion of the atom called? Nucleus. What the electron is doing? Electron is revolving in the nth orbit with velocity v, with radius r. It is moving in the circular track. So electron is moving in the nth orbit of the atom of radius r. Whenever this electron is moving, please remember, whatever the centripetal force is there, that centripetal force, which is given by mv squared by r, is provided by the electrostatic force. What is the electrostatic force? 1 by 4 pi epsilon naught into Ze squared by r squared. So what is the first postulate of the Bohr's theory? Whenever the electron is revolving in the nth orbit of atom, the centripetal force required for the electron to revolve, that centripetal force is provided by the electrostatic force between the nucleus and the electron. Now, whenever this electron is revolving in particular orbit, in all the orbit, the electrons will not revolve. In all the orbits, the electron will not revolve. Those orbits whose angular momentum, what is angular momentum? MVRN. Those orbits whose angular momentum MVRN is equal to an integral multiple of h by 2 pi. In those orbits, only the electrons will revolve. Such orbits we call it as stationary orbits. So please remember, the necessary centripetal force, is equal to the electrostatic force between the nucleus and the electron. And in all the orbits, the electrons will not revolve. In those orbits whose angular momentum, is equal to an integral multiple of h by 2 pi. In those orbits, only the electrons will revolve. Such orbits we call it as what? Stationary orbits. Then, whenever the electron is jumping from higher orbit to lower orbit, it emits the energy which is given by the formula E2 minus E1 is equal to h nu or hc by lambda. So when electron jumps from higher orbit to lower orbit, when electron jumps from higher orbit to lower orbit, it emits the energy. That energy is given by the formula E2 minus E1 is equal to h nu or hc by lambda. So please remember these three postulates. Using these three postulates only, we are going to discuss the another three important concepts, that is radius, velocity, and the total energy. So the first one, let us take, that is the radius of the orbit. Now, if I consider this is the nth orbit, if I consider this as the nth orbit, if the electron is revolving in the nth orbit, then the radius of the nth orbit is given by the formula. Please remember, the radius of the electron in the nth orbit is given by the formula epsilon naught into n squared into h squared divided by pi m z e square. So what's the formula for the radius of electron in the nth orbit of hydrogen atom? Epsilon naught n squared h squared divided by pi m z e squared. If you are using a hydrogen atom, then you have to take the value of Z as 1. Because for hydrogen atom, the atomic number Z is 1. So the radius of the nth orbit of the hydrogen atom will come to be what? Epsilon naught n squared h squared divided by pi m e squared. So what is the radius of the nth orbit in the hydrogen atom? Epsilon naught n squared h squared divided by pi m e squared. So please remember this. If you look at the orbit number n, can you tell me how the radius of the nth orbit and n are related? Radius of the nth orbit is directly proportional to the square of the principal quantum number, that is orbit number n. So as the orbit number n increases, the radius of the nth orbit also increases, and the radius of the nth orbit is directly proportional to square of the orbit number. Got it? Suppose if I calculate the radius of the first orbit of an hydrogen atom, please remember the radius of the first orbit of hydrogen atom is 0.53 angstrom. What is the radius of the first orbit of hydrogen atom? The radius of the first orbit of the hydrogen atom is 0.53 angstrom. Now, can you tell me what is the radius of the second orbit? At least can you tell me how many times of R1? R is directly proportional to n squared, isn't it? So if you want the radius in the second orbit, how many times I have to do? 2 squared times of the radius of the first orbit. What is the radius of the third orbit? 3 squared times of R1. So in general, if I go with radius of the nth orbit, then please remember it is n squared times of R1. So if you know the radius of the first orbit, you can find what is the radius in the nth orbit. The radius in the nth orbit is equal to n squared times of R1. So this is how you are going to find the radius of the electron in the nth orbit of hydrogen and hydrogen-like atoms. Please remember the general formula, that is epsilon naught n squared h squared divided by pi m z e squared. Yeah. Come to the second one, that is the speed of the electron. Whenever the electron is moving with velocity v, what is the velocity formula? Please remember the velocity formula, which is given by the formula z times of e squared divided by 2 epsilon naught nh. What is the velocity of the electron in the nth orbit of atom? Z e squared divided by 2 epsilon naught nh. If I want to find for the hydrogen atom, the value of z is equal to 1. So this implies velocity is equal to e squared divided by 2 epsilon naught nh. So what is the velocity formula for hydrogen atom? It is e squared divided by 2 epsilon naught nh. Can you tell me what is the velocity in the first orbit? Yes. Radius of the first orbit is 0.53 angstrom. Correct? No. Then what is the velocity of the first orbit? It is 2.2 into 10 power 6 meter per second. So what is the velocity of the electron in the first orbit? It is 2.2 into 10 power 6 meter per second. Therefore, what is the velocity of the electron in the nth orbit? It is v1 divided by n, because velocity and orbit number are inversely proportional. So velocity is inversely proportional to the orbit number. As orbit number increases, the velocity of the electron decreases. So velocity of the electron in the nth orbit is equal to v1 times of 1 by n, or you can say v1 divided by n. And also you can remember the velocity of the electron of the hydrogen atom to the speed of light is always equal to 1 by 37 ratio. So what is the speed of the electron? What is the speed of the electron in the first orbit of hydrogen atom to the speed of light ratio? That is v by c, that is 1 divided by 137 times. Got it? Yeah. Now, let us consider an atom. This is the nucleus. This is called the radius of the electron in the nth orbit. The velocity of the electron moving with the velocity is v. You know the formula for the radius, which is given by the formula epsilon naught n squared h squared divided by pi m z e squared. What about velocity? Z e squared divided by 2 epsilon naught nh. 2 epsilon naught nh. This is the formula which you have studied. Now, let us have a discussion one by one. First thing, I have to calculate the concept of the time period. Time period, capital T. Now, can you tell me how to find out the time period T? Time period is nothing but the distance covered, that is 2 pi r, with the velocity 2 pi r by v. So t equals to 2 pi. What about r? Epsilon naught n squared h squared divided by pi m z e squared. Whole thing divided by the velocity. What is that velocity? Z e squared divided by 2 epsilon naught nh. Now I can cancel with this pi and pi. Correct? No? Then this 2 epsilon naught nh will goes to numerator. So t will becomes what? 2 into 2 will be 4. Epsilon naught into epsilon naught will be epsilon naught squared. nh into n squared h squared will be n cube h cube. Whole thing divided by m z squared e power 4. So this is the formula for the time period. But I want to give the conclusion that the time period t and n are directly proportional to the cube. Time period is directly proportional to cube of the principal quantum number. So this clearly tells as orbit number increases, the time period also increases. So time period is directly proportional to n cube. This is very important, Appa. How the time period and the principal quantum number, that is orbit number, are related. Time period is directly proportional to the cube of the principal quantum number n. So this is how we are going to find the time period of the electron. In the competitive, they will ask you to find the time ratio by giving the first orbit and the second orbit. So if you know the orbit number, easily you can find the time period ratio, because time period is directly proportional to n cube. Now, can you tell me how the frequency and the time period are related? Frequency is inversely proportional to the time period. So frequency is inversely proportional to 1 by n cube. Frequency is inversely proportional to 1 by n cube. Because you know that the frequency and the time period are inversely proportional. Also, you know that angular frequency omega is 2 pi f. So that is, you can tell omega is directly proportional to frequency, which is inversely proportional to n cube. So omega is equal to 2 pi f. So omega is directly proportional to f, and it is inversely proportional to 1 divided by n cube. Remember that. So this is about the concept of the time period, the frequency, and the angular frequency. Got it? Yeah. Come to the next very important concept, that is the energy of an electron in the nth orbit. Suppose if I consider the nucleus at the center and the electron which is revolving in the nth orbit with velocity v and the radius rn. whenever the electron is there in the nth orbit, it will possess two energies. One is called the potential energy and the another one is called as the kinetic energy. What's the formula for the potential energy? Potential energy is given by the formula, please remember, minus m z square e power 4 divided by 4 pi epsilon naught. 4 pi epsilon naught, or on simplification I can write, further simplification, 4 epsilon naught squared n squared h squared. So potential energy is given by minus mz squared e power 4 divided by 4 epsilon naught squared h squared n squared. After simplification, after putting the radius value, we'll get this final expression. What you will get for kinetic energy then? Kinetic energy will be positive m z squared e power 4 divided by 8 times of epsilon naught squared n squared h squared. This is kinetic energy. If you know the potential energy and the kinetic energy, you can find the total energy. The total energy is the sum of potential energy and kinetic energy. So the sum of these two energy is going to be minus mz squared e power 4 divided by 8 epsilon naught squared n squared h squared. So what is the total energy? Minus mz squared e power 4 divided by 8 epsilon naught squared n squared h squared. So please remember these three different formulas. Now, can you look the formula for kinetic energy versus the total energy? Kinetic energy and the total energy are same, but please remember it will be a negative times. So total energy is negative times of kinetic energy. And total energy is half times of potential energy. Whatever the potential energy we have, you have to take half times of that. So total energy is half times of the potential energy. So total energy is equal to half times of the potential energy. So on this comparison, you can also tell kinetic energy is half times of potential energy with minus sign. So kinetic energy will be minus half times of potential energy. Please remember the relation between this total energy, kinetic energy, and the potential energy. Correct? Yeah. Suppose if you want to find for the hydrogen atom, for the hydrogen atom, Z value will be 1. Then the total energy in the nth orbit of the hydrogen atom is given by minus m z squared. Now for hydrogen atom, what will be the value of Z? 1. So minus m e power 4 divided by 8 epsilon naught squared n squared h squared. So Z value I'm going to consider as 1 for hydrogen atom. Can you find what is the energy in the first orbit? Energy in the first orbit means you have to put n is equal to 1, and you know all these parameters which are all constants. On substituting that, we will get it as minus 13.6 electron volt. What is the energy in the first orbit? Minus 13.6 electron volt. Now, can you find the energy in the second orbit? Minus 13.6 divided by what? Have a look. This energy and this orbit number are inversely proportional. Energy is inversely proportional to n square. So whatever the E1 value we have, for that you have to divide by 2 square, that is 4. What about E3? Minus 13.6 divided by 3 square, that is 9. So in general, what is the energy in the nth orbit then? Whatever the energy we have E1, for that you have to divide by n square. So what is the energy in the nth orbit? Energy in the nth orbit is equal to E1 divided by n squared. E1 divided by n squared. This is the energy in the nth orbit of an electron in the hydrogen atom. That is E1 divided by n squared. So this is how the energy orbit is going to be there in the nth orbit in terms of E1. Got it, students? Yeah. I will stop at this stage. In the next class, we'll take up the spectral series of hydrogen atom so that I can share that in the normal this thing up instead of this tab. I'll go with that screen sharing so that it will be a better for you. Okay. So I will stop at this stage. We'll continue in the next class. Thank you.
Thank you, sir.